Welcome to this explainer. Today, we're putting on our hard hats and acting as digital architects. We are going to use the ultimate blueprint to build a fully functional computer processor from the absolute ground up. If you've ever wondered how the microscopic logic inside your devices actually comes together to perform complex tasks, you are in exactly the right place. We're going to take abstract computer science concepts and turn them into a visual working machine. So why does all this matter right now? Well, we're basically looking at an open-source, royalty-free revolution. Historically, instruction set architectures, the language that allows software to talk to hardware, were proprietary and super expensive to license. But RISC-V changes all of that. Backed by tech giants, universities, and even DARPA, this open standard fundamentally removes the financial and legal barriers to entry for CPU design. It's freely available. That means anyone, from a small IoT manufacturer to a curious student, can experiment with a proven world-class computer architecture. To actually build and visualize this open-source architecture today, we're using a brilliantly clever tool called Logisim. Instead of just writing code or staring at dry electrical engineering equations, Logisim turns circuit design into a visual, simulated construction site. You can drag and drop gates, wire them up, and literally watch the data flow through your processor in real time as you build it. It is absolutely the best way to bridge the gap between theory and reality. Here is our blueprint for this explainer. We're going to cover the open-source CPU revolution, the foundations of digital logic, the brains of the operation, memory and CPU workflow, and finally, how to avoid some common design pitfalls. Let's get to it. Section 1. The open-source CPU revolution. Before we start wiring up the individual components, let's take a look at our majestic final destination. This seemingly chaotic web of wiring, that is actually our fully assembled 32-bit RISC-V CPU. I know, it looks incredibly intimidating at first glance, with wires crossing, sub-circuits glowing, and data pins everywhere, but I promise you, by the end of this explainer, you'll understand exactly how this machine breathes. It's really entirely made up of smaller, highly logical subsystems that just work together in perfect harmony. To get to that final product, our assembly line really only requires 6 fundamental organs to be integrated together. We've got the program counter logic to track where we are, the register file for lightning-quick data access, instruction memory and data memory for storage, the arithmetic logic unit for the heavy math, and the decode logic to act as the traffic director translating instructions. That's it. Just 6 components to make a computer think. Moving right along to Section 2, Foundations of Digital Logic. To understand the whole machine, we've got to zoom way into the microscopic level. And the most important brick in our foundation is the D flip-flop. It acts as what engineers call a bistable multivibrator, which is really just a fancy way of saying it's a switch with 2 stable states. Using a clever arrangement of logic gates, it's able to capture and store just one single bit of information, a 1 or a 0. Whenever the clock ticks, it updates its stored value based on the incoming data line. It is literally the absolute bedrock of computer memory. And this perfectly illustrates how we scale things up. By simply linking those individual D flip-flops together in a row and tying them to a shared clock signal, boom, we create a register. Here we're looking at a simple 4-bit register, but this concept scales infinitely. If we string 32 of these together, we have a 32-bit register capable of storing whole words of binary data at the exact same moment. This is exactly how a CPU holds onto the numbers it's currently thinking about. Section 3. The brains of the operation. With our temporary storage handled, let's look at the actual mathematical brains of the computer, the ALU, or arithmetic logic unit. You can see it's a wonderfully complex subcircuit responsible for carrying out all the heavy lifting. When your CPU needs to perform additions, subtractions, logical left or right shifts, or bitwise operations like AND, OR, and XOR, it sends the data here. The ALU receives 2 operands, basically 2 numbers, and based on the specific instruction it gets from the CPU's decoder, it routes those numbers through the correct mathematical gates to produce a result, instantly. But wait, how does the ALU, or any part of the CPU for that matter, know what to actually do next? Well, for that, we use a program counter, or PC. I want you to think of the PC exactly like your own index finger pointing to the current word you're reading on a page. In its natural state, it just increments, moving forward line by line, instruction by instruction. But if the code dictates a loop or an if statement, the PC can jump backwards or skip forwards to a totally new paragraph of instructions. It's the navigator of our entire processor. Which brings us to Section 4, Memory and CPU Workflow. Now, having a brain and a navigator is awesome. but we need a vast library to hold all those instructions and the resulting data. In this architecture, we split our memory into two distinct banks, both built upon the foundation of those registers we discussed earlier. On the left, we have the IM, or instruction memory. The CPU only ever reads from this bank. It contains the fixed program code. On the right is the DMEM, or data memory. This is your working scratchpad. The CPU can both read variables from it and write newly processed data back into it. Keeping these separate ensures a super smooth, uninterrupted pipeline of data flow. When we finally flip the switch and turn the simulated power on, this beautiful 6-step loop runs continuously. First, the program counter points to an address in the IMEM. Second, that raw 32-bit instruction is fetched and decoded. Third, the register file provides the necessary data values. Fourth, the ALU crunches the numbers. Fifth, the result is either written back to a register or stored safely in the DMEM. And finally, sixth, the clock ticks, the PC updates, and the cycle seamlessly begins all over again. It is a perfectly orchestrated digital symphony. And finally, Section 5, avoiding common design pitfalls. Now that you know how the machine ticks, let's pivot to some insider pro tips on what not to do when building your own. First up is a classic beginner mistake. Avoid the bad practice of using manual constants and splitters to extend binary numbers. For example, if you need to turn a 12-bit number into a 32-bit number, please don't just glue 20 zeros to it manually. Always keep your blueprints clean and efficient by using a dedicated bit extender module. It makes your circuit dramatically easier to read and inherently way less prone to wiring errors. Similarly, you should constantly be looking to optimize your logic gates. Do not overcomplicate your design by taking a multiplexer, feeding a signal into one pin, and the inverse of that signal into another. Honestly, that's just incredibly redundant. This behavior can be far more elegantly and efficiently achieved with just a single XOR gate. Remember, minimalist design is good design. Also, when you're laying everything out, think of your wires like physical plumbing in a house. You would never run a water pipe straight through the middle of a television set, right? So in Logisim, wires should never cross through a component. They should always be neatly routed around your subcircuits. Unlabeled messy wiring is just like writing code with zero comments. It is an absolute nightmare for anyone trying to understand your logic. And finally, we have a quirky but absolutely essential rule for the Logisim software itself. The default orientation of this program assumes that data naturally flows from the left side of your screen to the right side of your screen. Primitives are aligned this way, and certain components just don't rotate well. Save yourself a massive headache and an ugly diagram. Don't fight the software. Design your overarching CPU architecture to naturally flow in that left-to-right direction. So, armed with this structural knowledge of how a RISC-V CPU operates under the hood, and with these expert design best practices in your toolkit, the only question left is for you. If you had free open-source access to the world's most proven computer architecture, what incredible device would you simulate next? The barrier to entry is officially gone, and the blueprint is yours. Thank you for joining me on this explainer, and hey, happy building!